So let's go ahead and get started. So we can imagine, let's start in the beginning, that, a lot of times when we draw cyclohexane, first of all, it has how many carbons? 6. Kind of looks like that. Okay, that's the way that we often draw it. Okay, however, that doesn't really do a very good job of talking about it in 3 dimensions. That's also assuming that's planar. Okay, so we can imagine that there are, at the 2 extremes, there are 2 different ways of drawing cyclohexane. Okay, so one conformation is called the boat. Or as my people like to call it, the canoe. Ugh, I don't like that one. Okay, so if I look at this, the boat conformation is the easiest one for me, or the easier one of the 2 to do on the models. So you can see why it looks like a boat or canoe for those of us of that persuasion. And so because you can sit in here, la 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 la, oh, and so that's one extreme. The other extreme is called the chair. And the PowerPoints, which this PowerPoint is not up on MyFire yet, it goes through painstakingly on how to draw like the perfect chair. As long as I can tell that you're drawing the chair, then it's all good with me, okay? Because I don't draw the perfect chair. But so that's why on the chair, whenever I do the chairs, I definitely put in the little circles, because technically speaking, they're all supposed to be the same length. Okay, but it kind of looks like a chaise lounge. So like the way that you'll see in the PowerPoints is it says draw 2 parallel lines, then draw 2 more parallel lines going at an angle, then draw the lines to connect them. But when they do that, to me, it doesn't really look like a chair. But actually, that's not too shabby. Let me see, where's the eraser? Okay, these are the 2 extremes. Like I said, that one's not very good. Okay, so remember, this is the boat. This one's the chair, which the chair it's much more difficult to do. Let's see, up, down, up, up. There we go. 3 up, 3 down. So, like, whenever you do it this way, which is kind of like the way that well, I already erased it. They kind of draw it to show you, oh, that's the chair. But it's kind of hard to tell. Whereas if you kind of turn it on its side, now you can kind of see that, oh, that's the chair. That's the reason why it's called the chair conformation. And it's easier to say chair than chaise lounge. All right. One of these 2, like I said, these are the 2 extremes. You can have really almost anything in between. Like they talk about the half chair and all that kind of stuff. But we can have almost anything in between. And I don't expect you to memorize the numbers, like which one, I want you to know which one's more stable, but not necessarily say, oh, and I'm going to make this number up because I don't even have it memorized, but it's 8.6 kilojoules per mole more stable. That's not important. I just want you to know and be able to understand the rationale, the logic behind why one of them is more stable than the other one. Okay? So one of these, not in this necessary particular order, so you may want to just wait to draw it until later. And you can, just as I've been doing here, messing around with it, you can flip from one to the other. It's called ring flipping. Okay, so you can do that if they move, because you have rotation around those bonds. One of these, maybe here, whoops, let me turn this back on. So once again, if we're going to look at the energy diagram, and once again, don't assume that one is one or the other. So this is just the flipping process as a function of free energy. Or even if you don't like G, you can talk about E for energy. It doesn't matter so much. Or heats of combustion, because that's what they like to use a lot of times. Okay. Then one of them may be here. First of all, you always have to, just like for me to move this from one to the other, I have to add energy. Okay. So one of them may be here. You have to add some energy. One of them's a little bit lower. You add some energy and you can get it back. And like I said, technically there are little half chairs and stuff, but I just want you to know the two extremes. Try not to draw the half chair or the torsional twist or whatever it is that they call them. Which one do you suppose is more stable, the boat or the chair? It's the chair. And it's actually easier on the model here to see why the boat is less stable. Because once again, those bonds on my chair that I drew, it's supposed to be all the same length. They're not, but they're supposed to. But if I do the boat, so you can imagine, you got your passenger in there and everything like that. But you slow it down. But if you notice, these two hydrogens here are awfully close together. These two hydrogens are really far apart. Okay? And so you can imagine, especially if you ever added like a methyl group onto this, you would never, I shouldn't say never, but 1% of the time or less probably have a methyl group in these this position, because now you can see it gets really, really close, and so this is a more unfavorable. Whereas if you do, like I said, I have to kind of cheat down, up, down. Now we have, if you notice, 3 of the hydrogens are pointing up, 3 of the hydrogens are pointing directly down, and all the other ones are pointing out, like so. Like I really wish I could leave this up there. And if it helps you to do some type of dance in your seat and you're not bothering someone else in the exams, feel free. Okay. But you're right. This right here, it is the chair. This one right here is the boat. And this is the boat as well. And this one's the chair. The chair is just slightly more energetically favorable. Okay. And we'll see like the actual energy diagram later on, where they do a much better job than I do at drawing it. Now, I'm going to try to do a much better job of redrawing the chair. Okay? Because this is where you've got to be very careful. I don't care so much as long as I can tell that you're drawing the chair, that you draw all the bonds exactly the same length and everything like that. But these positions are not all created equal. Unlike men, they are not all created equal. No matter what some of our politicians say. And so, okay. Oh, come on now. So I'm going to try to really over-exaggerate this. And once again, I'm going to go ahead and put circles in so that way you can see my carbons a little better. All right. Okay. So, if you notice, and actually that's how I cheat whenever I'm making this model, is I say, oh, actually I can actually do it here. On one carbon, we have a hydrogen that's going up. So we may have a hydrogen going up. The next carbon is going to have a hydrogen going straight down. The next one's going to have one going straight up, straight down, straight up, and straight down. Okay, so now I'm going to put those in. I'm going to do those in a different color, so that way it's a little easier to see. These are not methyl groups, these are hydrogens. I'm just trying to let you see you have one going up. The next one's going straight down. straight up, straight down, straight up, and straight down. Then, if we look here on the model, we see this one's going straight down. The other hydrogen on that carbon, it's going up, but not straight up. It's going up at a kind of like a little bit of an angle, okay? Just slightly of an angle. The one next to it, when I rotate it, since this one's going straight up, it's pointing down, but it's not straight down, it's pointing down. I really wish, just 1 more inch. That's all we needed. And so I'll put that in a different color. So this one's going to be going just a little bit down, just a little bit up, little down, little up, little down, and a little up. They give these positions. Right now, these are all hydrogens. But we're going to talk about like what happens whenever it's not a hydrogen. Okay. So what's the color of this one right here, for those who can tell? The red? Okay, the red ones all have a special name. That position, whether it's pointing up or straight down, it's called axial. Oops, that's not red though. Okay, those are axial. Whereas the other ones that are going, they're not going straight out, but just a little bit down or a little bit up, those have a special name as well. And those are called equatorial. Oh, see, it won't let me do that. I have to do it different. So those are axial. Check. And equatorial. Okay, actually, let me see if I can move it right there. The way I think about this is it's sort of like a globe. You know, the axis runs up and down. I know the Earth is slightly tilted, but you know, it runs straight up and down, with the equator is the one that kind of goes, you know, side to side. Okay? So there's axial and there's equatorial positions. And one thing, I don't have enough room, but this chair can be converted to where this one that's going up, it can be ring flipped. First of all, it has to become a boat briefly, where it can go now down. Hopefully you get the idea. Where you can actually interconvert between the two. So what before had been one version. That one's going to be down. Nope, we can flip. They're the same, and they would be the same in energy overall. Right now, because they're all hydrogens. So the question becomes, what happens when it's not all hydrogens? Are they all created equal? Okay. So we're now going to put in just one. It's going to be methyl cyclohexane. Okay. So on the example that I have here, and actually I'm going to go ahead and give you a chance to, once you take a little bit of time, I'm going to be taking some time too. I want to draw the two chair conformations where one of them's got the methyl cyclohexane in the axial position, one of them's got the methyl cyclohexane in the equatorial position. Okay, so once again, just to try to make it really obvious where my carbons are, I'm going to put the dots in. That one wasn't too shabby. Now, what I strongly suggest that you do, because I've taken off credit so many times where people only draw the methyl. And especially if they're in a hurry, they draw it like this. Well, I can't tell if that's axial or equatorial. And just by you trying to think that you're going to get partial credit, I'm going to count it wrong. So that's why you don't want to do that. So what I suggest that you do instead is go ahead and draw in, and unless you tell me, this is one time where, unless you tell me otherwise, you can assume that everything's a hydrogen. I know that technically, normally we'd say, oh, those are all methyl groups, but I'm going to deliberately put CH3 in. And the reason why I'm not putting all the H's in right here is that way we can clearly see which one's axial and which one's equatorial. Okay, so by putting in all the axial and equatorial positions, and I mean, if you were worried about it and this was on a quiz or exam, you could say, unless noted otherwise, here it's a hydrogen, or you can put all the H's in. That's fine as well. Okay, now the one that was to flip it. Oh, and like I said, there is equilibrium. I don't want to give away which one is going to be right, but no, there is an equilibrium between the two. We just don't know which direction it's going to favor right now. So this one right here that was pointing up, when it gets flipped, it's now going to be equatorial, pointing a little down. Okay. And I'll show you what I mean by that in just a moment. Okay, and it doesn't matter which one of these where we put the CH3. I'm just going to put it at this, or here, I'll put it at this position. And so since it's pointing up right here, first of all, is that axial or equatorial? It's axial. So therefore, on the next one, when it flips, it's going to be equatorial. Okay. And all of the other ones are hydrogens. The only hydrogen I'm going to draw in is just this one right here for right now. So that way you can clearly see that what we have. One of these, and I can even label it, this was whenever it was axial. This is when it's equatorial. One of these is more stable than the other. And so I'm going to give everyone a moment to get caught up in drawing. Just ignore the little curly cube. Whoops, if you does that. Just in case for anyone who missed, what we're saying is 95% of the time it's going to be equatorial. Not 95 degrees percent. This is 5%. So if we're drawing the equilibrium arrows, this one will be the big arrow, this would be the smaller arrow. Okay? And the reason being, once again, is the fact that whenever, and it's kind of hard to tell here, but whenever we have the CH3 group, it's actually relatively close to everything else that's pointing up. Now, if it was one going down, all of these are relatively close with respect to each other. However, not only is this one going down, but it's going away. So in 3 dimensions, that'd be a little bit of a hashed mark. And so it's going away from whatever is next door, adjacent to it. Okay. So now what would happen is, let's look at, let's draw 2 more. If we look at something that looks like, first of all, draw 2 chairs. So we do this over and over again. You'll be a pro. So now if we wanted to add a T-butyl or a methyl ethyl group, remember, if this was the point of attachment, this is what it's going to look like. And now these really are CH3s. Those are not hydrogens, okay? So we would have an option of having it look like this, or so once again, I'd expect you to know which one's axial, equatorial. So the way I have it drawn here is the T-butyl group, or the functional group paying off. On the one on the left is that axial or equatorial. Axial, and so the one on the right has to be equatorial. Which one is going to be more stable and be favored? The one that's axial or the one that's equatorial? It's equatorial, okay? In fact, it's greater than 99.99% of the time. So, I mean, it's almost 100% this way. So that's less than, that's greater than. So this would be less than 0.01%. Okay. So that's pretty simple. Hopefully I haven't lost anyone so far. So what happens if we have more than one thing? Okay, so now we're going to start thinking about what happens if we have more than one thing hanging off. This becomes a little more tricky. Okay, and so this is where I want to explain something called cis and trans. These are types of stereoisomers. So if you think back to Gen Chem 1, a stereoisomer had all the same linkages, but the ones that you probably learned about, I'm trying to think about I don't remember if you covered cis and trans in Gen Chem 1 or not, but you may have learned like your right hand and your left hand, how those are same linkages, but they're different ordered where they're non-superimposable and all that kind of stuff. So what I mean by that is this time I'm deliberately not going to be drawing the chair. Okay. So we could imagine I'm going to draw just the normal to where, because a lot of times if I draw it this way and try to talk about cyclohexane, people get a better feel and a better idea of what I mean. So if we do 1,2-dimethyl cyclohexane, it doesn't really matter. We just have, there are going to be two methyl groups on the same, on adjacent carbons, okay? And so you probably, don't do this part, but you probably would just draw it like this and that's fine, okay? But we're not thinking about 3 dimensions here. Same connectivity, but different three-dimensional space. You can imagine, what if we had both of these like coming out above the plane, okay? Or you can imagine you have one coming out towards you and one going away, right? These are stereoisomers with respect to, they have the same connectivity, they just differ in three-dimensional space. Okay, so that's all you're assuming, you haven't had like a bad woodshop accident. You have the same connectivity between your left hand and right hand, but they differ in three-dimensional space in that sense, okay? These are actually mirror images. So the way that this is drawn is the one that has both the methyl groups on the same face, the same side, is called cis. This is a cis stereoisomer. The one that's opposite is called trans. Okay. I'm going to give everybody a moment to get caught up, because now what I want us to think about is what happens if, let's look at a disubstituted cyclohexane, but now we also have to think about anytime we look at disubstituted cyclohexanes, whether the two groups are cis or they're trans. Okay, so let's just do trans. Let's do the trans isomer. So I'm going to erase this so that way, because I think that if I try to get rid of it, no, it didn't. Okay, it's good. So I'm wanting us to draw the trans 1, 2. And if you were naming it, by the way, you would actually name it trans, and technically they put it in italics in case you couldn't tell. Be trans dash 1, 2 dimethyl cyclohexane. So I want to give you guys a moment to draw your chairs. All right. So now we have to draw. And I'm going to just erase the. Whoops, that is not it. Let's see, it won't let me. So just ignore that one that says cis right there. I didn't pay any attention, and there we go. That gives it some more space. So let's now put in the cyclohexanes. So it doesn't matter to me which one we start off with. So I'm going to do, if we call this one position number 1, where is going to be position number 2? Do we have only one place that's position number 2, or we have 2 places? 2, because you can either count clockwise or counterclockwise right now, because there's only 2 things. So I have more room to draw if I put it on the one that's on the just below that. Okay, you could technically you can draw on the one just to the right, because that'd be 1, 2 as well. So if this is trans, that means it has to be on opposite sides. So would the methyl group be here in the equatorial position, or is it going to be here in the axial position? It's axial. Okay, now we're going to flip it. We do our little mumbo jumbo and we flip it. So this methyl group, which before had been axial, is now going to be equatorial. Whoops. And please note, I'm going to do something to show it's the carbon that is attached directly. And likewise, the same thing here. So, now we have to try to figure out, these are not created equal. Of course, that would be too easy. Which one is going to be more stable? The one on the left or the one on the right? It's the one on the right. Okay, and it's because, once again, we have to think, these look so far apart versus the other 2. But, so first of all, I'm drawing the one that's more stable, because they're both in the equatorial position. Because when you draw like that, it looks like the 2 carbons are really close together. But in reality, they're far apart. They're as far apart as these 2 that are on opposite ends of the circle, so to speak. Because remember, they're pointing out and away from each other, either out and down or out and up. And so they're also far apart from here. So there's actually a considerable distance, and they are also far away from all these other things. Whenever we deliberately put them on the 2 axial positions, now we've got, and I'm just going to show it for one, we've got the hydrogen here interacting here and with here, and we also have the interactions here at the bottom. Okay, so I don't know the exact percentage, and I wouldn't ask you to know the exact percentage, but just remember, it's best to have the big groups in the equatorial positions versus the axial positions, even though it's misleading whenever you draw it this way out there, because it's a 2-dimensional drawing. So that's why you have to start to think about what would that look like in 3 dimensions. And so if you're going to put in the arrows, it's going to favor like this. And it's going to be greater than 95%, because if it's 95% for 1, that's going to be greater than 95% most likely for 2, but you don't have to worry about that. So this one would be the major contributor. This one would be minor. Right? So that was trans 1,2-dimethylcyclohexane. Now let's do cis 1,2-dimethylcyclohexane. Just for time's sake, I'm going to write it out. So cis 1,2-dimethylcyclohexane. I'm going to give everybody a moment to draw your... In fact, this time I want you to go ahead and just draw it all the way out, and I'll do the same. So I've only put one of the methyl groups in. So if we look at this first one, it's in the axial position. And I'm going to use this carbon right here once again for carbon number 2, just because of the fact that I have more room there. But you could use this carbon. It's also carbon number 2. So for this to be cis, where should the other methyl group be? Should it be in the equatorial position or should it be in the axial position? Pardon? It's equatorial. And the reason why is, once again, and sometimes people get confused by this, this one's pointing straight up, this one's pointing slightly up, but they're both going up. So if you think about, remember the chair is not perfectly planar, but they are both going above the median plane of the chair, so to speak. All right, so now on the second one, is the methyl group on the carbon number 2, is it going to be axial or equatorial? It's going to be axial. Okay, so my question here is, which one of these is more stable? They're the same. They're identical. And the reason why is just literally added up. We have one axial, one equatorial. We have one axial, one equatorial. They're the same size, so we don't have to worry about that. And so therefore, they're equal. Okay? In fact, they're identical structures. They're not even considered to be different. They're considered to be the same structure. Okay, and the one that I want to leave you off with is what happens. Let's see, let's do. Oh, whoops, I didn't realize it's going to leave the. Let's do a trans. 1 ethyl. And this time let's do 3 methyl. And I'm only putting the hyphen there because I don't have enough room to write out cyclohexane. Okay, otherwise, you would just say methyl cyclohexane. But trans, 1 ethyl, 3 methyl cyclohexane.
Where's to draw both or just the most stable?
I want you to draw both.
Okay.
Mm-hmm. And then the question is one of them more stable or are they equal in stability? Because as we can see, there are times that you can have things that are disubstituted that are equal in stability. Not always, but sometimes. Okay, so we're going to actually leave this on a cliffhanger, so to be continued until next time. I know you'll lose sleep over it, I'm sure. But when we come to the next class, what we're going to do, you'll probably have to remind me which one I did, because fortunately the video won't let me pick up right where I left off, I don't believe. But then we'll discuss it. So on your own, you can actually sit down and try to figure it out, but we'll definitely discuss it further. So I'm going to go ahead and end class with prayer.